there are two things that in everything I said I was taking as given. One is the group composition, so I was considering a couple, but I was not asking why is it that this particular person ends up being married with that particular person. And then the decision process was described by Pareto weights, but those Pareto weights, they were considered as given, and the question was, can I recover them from observed behavior? But what was missing was a theory of the determination of those Pareto weights, and actually what's missing is a joint theory of group formation, so who marries whom, and of the determination of those Pareto weights. So in other words, what I would like is the inequality within the group to be an endogenous phenomenon, to be determined by something else. There are many ways in which you can do that. You can use matching model, you can use search model, you can use bargaining theory. Bargaining theory, we've been working on bargaining theory. In principle, it's quite an interesting tool. The problem with bargaining theory is the following. So you want to think about the respective power of the husband and the wife. A bargaining model seems like the natural way of thinking about that, right? Of course, bargaining, you need to be very precise about the reservation utility, about what the threat point. The problem is that, in a sense, you cannot escape what I would call the general equilibrium nature of the problem. In other words, take a couple who is about to marry. Let's take a simple vision in which couple make an agreement when they marry, and then what we observe in terms of Pareto weights is the outcome of this agreement. So essentially, I'm assuming some form of commitment. So when they bargain at the moment of marriage, what's the threat point? Well, obviously, the threat point is remaining single, but it could also be marrying somebody else. The problem is, if I want to write a bargaining model to understand how much the wife is going to get of the surplus and how much the husband is going to get of the surplus, I need the threat point, but the threat point is what they would get if they were marrying somebody else. And of course, what they would get if they marry somebody else is endogenous, and it might be a bargaining model, but then my current marriage is the threat point of this other model. My point here is simply, when you have an equilibrium, both the allocation and the threat point is determined simultaneously. And so it's not you, so in that sense, what's very promising is to use some kind of equilibrium concept or an equilibrium model in which both the threat points and the outcomes are determined simultaneously, which both matching model and search model are doing. I'm going to talk today exclusively about matching models. Both are interesting, and there is a very interesting research question, which is, when is it better to use search model? When is it better to use frictionless matching models? Again, it's a difficult question. Let me just give you a comparison. Think of a situation in which you want to look at the market for a given product, and you have supply and demand. There is a simple way, which is, there is a supply curve which is upward sloping, there is a demand curve which is downward sloping, they cross at some point, that will give you the price and the quantity. That's the kind of frictionless version of it. On the other hand, you could be much more precise than this, and you could say, but wait, there are frictions. For instance, all people don't face the same price. There is horizontal differentiation. People are not located at the same place, so there will be a price differentiation linked to the fact that some people have to move to go to a place. That if you're located at a place where there is a large demand, you can afford to charge higher prices, things like this. There are plenty of there informational friction. Not everybody is informed, and so on and so forth. For some problems, you can just disregard those friction and think in terms of supply, demand, price, quantity. For other problems, on the other hand, the frictions are crucial. Well, it's pretty much the same in those kind of equilibrium model. If you're a labor economist and you're mostly interested in unemployment, you want to use a search model because a large fraction of unemployment is due to frictions, and therefore you will never consider a model without frictions. On the other hand, if you're a labor economist and you're interested in the following question, what's the allocation of firms to, of workers to firms? Is it the case that the more productive workers go to the more productive firms? Or is it the fact that they go to larger firms? Or anything else? Is it the case that risk-averse workers tend to go to less risky firms and so on? It might make sense to disregard the friction and just look at the pure matching. So it's pretty much that's pretty much the spirit. You can look at all those questions from a search point of view or from a matching point of view. Today, just for the sake of brevity, I'm going to talk exclusively about matching model. I will talk a lot about transferable utility, although I will try to say a few words about what you can do without bargaining, without transferable utility. So essentially, I'm going to talk about matching models. Another thing is, I'm going to talk about intra-household, so the matching will be matching on the marriage market. The exact same tools that I'm going to present here could be used on the labor market. They could be used on matching between firms and banks. And actually, there is some ongoing work which is quite interesting. There are plenty of situations which correspond to matching models in which those kind of tools can be applied. And in particular, one of the things I'm going to emphasize is that there is a vast literature on hedonic models, and there is basically no difference between matching models and hedonic models. And so everything that I'm going to say about matching models applies to hedonic model, and this I'm going to clarify later on. I don't know how many of you are familiar with the literature on matching. As seen from the outside, it's extremely confusing. One thing, for instance, you might know, I mean, most of you must know that in general, people talk about transferable utility and non-transferable utility, so-called TU and NTU. And you might believe that those are the two cases, that you're either in a TU framework or in an NTU framework, which is absolutely not the case. Both TU and NTU are extreme cases, and there is a general case which I called imperfect TU, ITU. So the pure NTU framework, that's Gail Shapley. In all cases, you got two populations. Let me call them men and women. And in all cases, what you call a matching is you take a person from one population, you match that person with a person from the other population. In the NTU, such a matching generates two utility, one utility for the wife and one utility for the husband. And those are given. There is no way you can transfer between the wife and the husband. There is no technology that will allow you to decrease the utility of the wife and increase that of the husband, and conversely. It's a technical assumption. It's not an assumption on contract or anything. It's just you cannot transfer. That's the NTU case. The other extreme is the TU frameworks, that's Baker, Shapley, Shubik. Not only you can transfer, but you have a technology that can transfer at the constant exchange rate. By which I mean, so there is my utility, there is my wife's utility, and there I can transfer, for instance, private commodities, or I can transfer things that have to do with the choice of public consumption. There is a way in which I can decrease my utility and increase the utility of my wife. And there are ways in which I could increase my utility and decrease the utility of my wife. So in other words, there is something like a Pareto frontier. However, this Pareto frontier is a straight line with slope -1. That's the TU assumption, which means that the exchange rate between my utility and my wife's utility, the utility that the number of utiles that I need to give up in order to increase my wife's utility by 1 unit, is exactly what always, is exactly 1 always, whatever prices, whatever incomes, whatever the environment. That's the other extreme. So in the NTU case, you cannot transfer at all. In the TU case, you can transfer, and you get this kind of magic technology that has an exchange rate equal to 1. And then you got the general case, which is the ITU, and the ITU is a situation in which you can transfer, but there is a Pareto frontier which is continuous, but it's not a straight line, and so the exchange rate might change. Now, let me briefly summarize those three families, their similarities and their differences. So what are the familiarities? First of all of them want to explain who's matched with whom. In addition, the last two, and that's really what I'm interested in here, will explain how the surplus is divided. So in other words, In the first one, in an NTU, the division of the surplus is exogenous, so there is nothing to explain, it's given from the outset. Whereas if you're in the TU or ITU framework, it's endogenous, and that's interesting because it's exactly the distribution of power within the household will be determined by the equilibrium condition. So essentially, it's about endogenizing power, endogenizing intramature location, and so on. The setting, I have two populations, the matching one individual from each population. Heterogeneity is the key notion here. Those models are useful when people are different. Of course, you can always formally use matching model when men are identical and when women are identical, but the benefit is nil. When women are all different, men are all different, and when matched together, they generate a surplus that's couple specific. That's exactly the kind of situation in which the complexity in which you need the matching technology. There are various generalizations that I'm not going to talk about. And finally, the concept. The concept is stability. Now, you're familiar with the notion of stability. We're talking about bilateral one-to-one matching. Stability is essentially robustness vis-a-vis uni or bilateral deviation. So a matching is stable if you cannot find a person who's married and would be better off being single, and you cannot find two persons who are not currently married together and who would both prefer being married together than what their current situation, whatever that can be. Standard notion of stability, okay? Now, let me be a bit more precise about this transferable utility. Most of my talk will be about this. It's a strong assumption, but it's an assumption that buys you that gives you a lot of mileage. So it's exactly, it's very important to understand exactly what you're assuming and exactly what the cost for those assumptions is. Here is the formal definition. A group satisfies transferable utility if there is a monotone transformation of individual utility such that the Pareto frontier is an hyperplane. The crucial thing here is transferable utility is an ordinal property. It's not a cardinal property. There exists a transformation such that it's an hyperplane. One of the reasons why it's important is there is a misconception that you find sometimes in the literature, which is transferable utility requires something like quasi-linear utilities. Quasi-linear utilities requires neutrality vis-a-vis risk, so you cannot use matching models to talk about matching risk from sharing risk sharing, for instance. That's completely false. And actually, I'm going to give you an example in which you use matching model to think about the way in which people match to share risk. It's an ordinal property, and you could, in addition, put any kind of cardinalization, and in particular, any kind of risk aversion that you want. The second thing is, if transferable utility works, the way it works, what does it mean that the Pareto frontier is a straight line with slope -1? Essentially, it means that any efficient allocation maximizes the sum of utility, which is quite different from the general case. The general case, you're maximizing a weighted sum of utility, but the weight can be different. Not in the TU. In the TU case, efficiency means that you're maximizing the sum of utility. So in particular, an implication of this is that there is unanimity regarding the group decision. When people talk in a TU framework, there is no problem about how much public good and how much private good they should buy, because there is unanimity about public good decision. They're going to take the choice of the public good vector, which maximizes total utility. Now, this is a strength and a weakness. It's obviously a weakness because the one thing you won't get in a TU model is, because of changes in the markets, the situation of the respective situation of women with respect to men is better, and therefore more will be spent on children, for instance. A TU model will never give you this, because in a TU model, how much you spend on the children does not depend on the respective power of the husband and the wife. On the other hand, so if you want to look at those kind of stuff, you need to look at these imperfectly transferable utility models that I'm going to talk about. On the other hand, the positive side is you have something like a very pure model of power, in the sense that there is a complete dichotomy in which between the aggregate behavior on the one hand and the intra-group allocation on the other hand. The aggregate behavior has nothing to do with intragroup allocation. It has to do with efficiency and maximization. On the other hand, the allocation within the family is completely driven by the power and by the equilibrium conditions. Now that's that general. What does it mean in the case of marriage markets? So in other words, is it compatible with the collective approach? Well, the collective approach, first of all, typically you have transfers. There are private consumption, there are public consumption. You can consume more or less of, I can consume more, my wife can consume more of the private goods. And also, if my wife cares more than I do about the public good, we can consume more or less of the public good. All these are transfers. But in general, in the collective model, the Pareto frontier is not a straight line, is a standard, the convex set. What do you need to assume in the collective framework to get this property that that we have a transferable utility? Well, this is necessary and sufficient, and this is in an old paper by Bergstrom and Korns in '81. So look at this functional form here. First of all, there is an Fi. The Fi is simply reminding you that it's an ordinal property, so you can compose it with any cardinalization that you want, right? Now, I have the sum of two terms. The first term is absolutely anything, except that it does not depend on the private consumption of one of the private commodity, which is commodity one. The second term, I have the private consumption of commodity one, and this commodity has a marginal utility that depends only on the public good. And in addition, this function Bi of Q must be the same for everyone. Now, what this is telling you is, if I give 1 unit of commodity one to my wife, the cost for me is B of Q, but the benefit for my wife is B of Q. So that's exactly what gives you the fact that the exchange rate is equal to 1. This is necessary and sufficient, so that's what you're assuming. So as I said, it's an ordinal property, and it's also it's a restriction on the form of each preference, and it's also a restriction of the level of heterogeneity. So, as I said, in the TU model, all Pareto allocation give the same aggregate consumption, in particular the same demand for public good, and efficiency is equivalent to maximization of total utility. Okay. Now, this is just an example. It's not, the fractional form might seem a little bit strange, but it's very easy to generate example that fit is. So let's take a simple model in which I have two commodity, one public commodity, which is capital Q, and one private commodity, which is small q, and I take Cobb-Douglas, slightly general version of the Cobb-Douglas. I mean, it's a linear expenditure system. This is compatible with the framework that I gave you before. So this is a model in which there is transferable utility. So the story is, if you marry someone with, if you marry a man with income Y with a woman with income X, you have a surplus. The surplus is the animal which is here, and the equation of the Pareto efficient frontier as the equation, the utility of the husband plus the utility of the wife is equal to the surplus. Let me say a few things about the general structure. This is think of this as a mathematical appendix, but it's quite important to understand, to get exactly the mathematical structure right, to understand what's going on. So I have two spaces. X is the set of female characteristic, and Y is the set of male characteristic. The crucial thing is, if X is everything I need to know to characterize this woman on the marriage market, and Y is exactly everything I need to know about the husband. Some of those characteristics might be unobservable, and actually when I take that to data, I will introduce the fact that there may be observable and non-observable characteristics. Also, the crucial thing is, I'm not assuming in principle that X and Y are one-dimensional. They can be many-dimensional. They can have as many dimensions as you want. Now, if you take Mrs. X and you marry with Mr. Y, there is a surplus, S of XY, and the only thing I need about the surplus is some minimum level of continuity. Actually, I need the upper semi-continuity. Now, what's a matching? Intuitively, a matching tells you who marries whom, And who marries whom should be a function, right? It should be, if you give me Mrs. X, she's going to marry Mr. Y, which is some function of X. That's not the way I'm going to put it. That's not the way the literature is putting it. And there are two problems with the notion of a function. First of all, when you say a function, you're assuming that the matching is deterministic. So if I'm saying Mrs. X is married with Mr. Y equal phi of X, I'm assuming that a given wife can be married only with one particular husband with probability 1. Well, in some models, it's not the case. In some models, the equilibrium involves mixed strategies in which the same woman can be married with different husbands, with each of them with positive probability. So I don't want to discard them from the outset. And the second thing is, this model has a lot of linearity properties that you might not see, but that you will see in a minute. So here is the way I'm defining the problem. A matching is a measure on the product set. Now, think just H is the measure. Think of H of XY as the probability that Mrs. X is married with Mr. Y at the stable match. This probability can be 0 for most couples, and it can be 1 for exactly one husband, but it could be 1/2 for 2 different husbands or things like this. The crucial thing with this measure is I know the marginal, because if I take a given X and I add all the couple in which the X is married with a Y for all the possible Y, what I will get at the end is the number of X people in the population, and that's given. So I have a measure on the product space, but the marginal are just the initial distribution of characteristic on the male space and on the female space. So essentially, this measure is telling me who's marrying whom in a probabilistic sense. But I need something else. I need to say, when people are married, how is the surplus distributed between them? So the definition of a matching is not only a measure, but two functions, u of x and v of y. So think of u of x as the utility that Mrs. X will get at a stable match. Think of v of y as the utility of Mr. Y will get. And the condition is that whenever two persons are married with a positive probability, so whenever x and y belong to the support of the measure, then it must be that what she gets but what he gets is the surplus. That's the definition of a matching, and this condition is a feasibility condition. You cannot distribute more than the pi that you generate. Now, what's stability? Now, stability is characterized by this inequality here. And let's try to think about what this inequality means. Assume just for a minute that instead of this inequality here, I have a strict inequality in the opposite direction. So assume that it's the case that some x and y are such that u of x plus v of y is strictly less than s of xy. This tells me two things. The first thing is that those people are not married, because if they were married, I would have an equality. If you have a strict inequality, they're not married. And the second thing is they should be married. They should be married because the size of the pi that they will generate by being married is more than the sum of what he's currently getting and what she's currently getting. So by marrying, they could improve the situation of both. But that's a violation of stability. That cannot be the case. So if I have stability, it must be the case that for each x and y, including and especially for those who are not married, what she gets plus what he gets is more than what they could do together. Are you following me? That's standard. Now, this is the main reason why transferable utility is a very tractable kind of model. Forget just for a minute my notion of stability, which is a kind of non-cooperative game theoretic kind of concept, and let's just talk about surplus maximization. Assume that you're the central planner of this economy. So you decide the measure, you decide who marries whom, and you try to decide in such a way as to maximize total surplus. Total surplus is just the sum of utility. In general, I'm not allowed to add up utilities, but in a TU I am, right? I'm using the cardinalization in which the sum of utility is for which I have this 45-degree line property, so I can talk about the sum of utilities. In particular, TU involves a very strong version of interpersonal comparisons of utility. Now, think of the following problem. I have two space, male, female characteristic, male characteristic. I know the measures. I have a surplus, and I want to find a measure H on X on the product such that the marginals are given, and I want to maximize total surplus. That's a standard problem in mathematics. It's called an optimal transportation problem. It dates back to Monge. The initial motivation, by the way, X was a set of mines, and Y was a set of factories. And the question was, you want to allocate the coal from the various mines to the various factory in such a way as to minimize total transportation cost, which is the reason why it's called an optimal transportation problem. So H of XY is the percentage of the coal coming from mine X and going to factory Y. Of course, the marginal are given because if you integrate of all the factories, you got the total production of the mine, and if you integrate of all the mine, you have the total demand of the factory. And you want to solve to S of XY is minus the transportation cost, and you want to maximize the integral of minus the transportation cost, which is minimize the total transportation cost. The crucial thing is this is linear. Remember, my unknown here is the measure. This max here is linear vis-a-vis the measure, and my condition on the marginals are also linear vis-a-vis the measure. So this is linear programming. This tells you right at the outset that my life will be very easy if I want to go numeric. If I want to use some kind of numerical simulation to solve my problem, the problem that I will face is a linear programming problem for which we have algorithms that go extremely fast. That's one cool thing with linear programming. A second cool thing with linear programming is that there is duality. If I have a maximization problem, I can look at the dual. Now, how many of you are able to write the dual of this model in full generality? It may not be used. I mean, I don't need finite support, that's the general mathematical theorem. But the point is, it's not economics, it's just mathematics. A primal model that's linear has a dual. Now, here is the dual. I'm trying to find dual function u of x and v of y that minimizes the sum of those two integrals here, and look at the constraint. The constraints are exactly my stability condition. Now, let me come back to the matching. Think of an old question in the matching literature, which is, can I find a stable match? In general, it's a very difficult question. And it's very easy to generate problems in which there is no such thing as a stable match. If you look at the problem which is here, using the stability criterion, it's easy to convince yourself that it's a very difficult problem because I'm trying to find two functions that satisfy a bunch of inequality. I have a very large number of inequalities here. Even if I have population of 1,000 men and 1,000 women, which is not a large population, by current econometric standard, I have 1 million inequality. Can I find 1,000 numbers u of x and 1,000 number v of y that satisfy 1 million inequality? It's by no means obvious. Actually, it's if everything doubtful. So if I want to address the problem of existence of a stable match, looking at this problem here, it's quite a difficult problem. But thanks God, I have my duality result. The duality theorem tells me if I have a solution to the primal, I have a solution to the dual, and the value of the solution is the same. But I know that I have a solution to the primal, because what are the constraints? I have a maximization, so I don't need much. I need some minimum level of compactness and some kind of continuity, and which is the reason why I assume this upper semi-continuity of the S function. And the existence, and then the constraints are just of the marginal. So is it possible to find a measure with given marginal? And the answer is yes, always. It's always possible to find a measure with given marginal. Just assume that the variables are independent, and that will give you a measure. It's not the only one, but there is one. So I know that there is at least one measure that satisfies the constraint. Actually, there is a very large number of measures that satisfy the constraint. I know that this maximization problem, under the assumption that I made, has a solution. So the dual minimization problem as a solution. So there exists functions that satisfy those inequalities. And we have this basic theorem, which is the matching is stable if and only if it solves the surplus maximization problem. Yes?
Could you go back to the stability condition? Or this?
Yes?
Yeah. I don't know. So the way I see it, why would it not be equality? One? I just don't see why the individual utilities would be larger than what they obtain together. If I'm just thinking. So I'm thinking about it from a Nash equilibrium. So why would they not divorce? Maybe it's notation. So are these?
Let me come back to here. If they are married with positive probability, it has to be an equality. If they are not married, it might be the case that what I get plus what my wife gets, what I get, we're not married together. This woman and I are not married together, and it so happened that if we were to marry together, we will get much less than what we currently have. I mean, if you were to impose equality for all x and y, in general, there would be no solution.
Okay, so but why, if they get more when they're not together, then why is the matching stable? Because if they get more if they're not together, then they would prefer to divorce.
Remember, x and y in this last inequality are not married together.
Okay.
And what this inequality is telling you, that's why they're not married together. They're not married together because if they were to marry together, what they will get will not be enough for them to be satisfied, in the sense for her to get as much as she could get and for him to get as much as he could get. So when you have a strict inequality here, this tells you stability implies that those people cannot be married at equilibrium.
Okay.
And the equality tells you if they are married, then I have this. Is that clear?
That's clear. Thanks.
Do you guys have other questions? I mean, it's crucial to really understand the logic of this.
Will actually hold. Sorry. In equilibrium, if the matching is stable, actually this inequality always holds. This is just a condition. It wouldn't be like a strict inequality.
Can you state it again?
For in equilibrium, if the matching is stable, actually for all the people that are married, this inequality always holds. So this strict inequality is just a definition for the stability concept.
Absolutely. That's a definition of the stability.
Okay, thank you. Then it's clear for me now.
If you have one violation of this inequality, then you can tell that the matching is not stable because you can isolate a couple that's not married and that should be married, which is a violation of stability. You get exactly right. Is the concept clear? Now, we have this general result that matching is stable if it solves the surplus maximization model. Now, you can do that. The nice thing is that you can do that in very general spaces. You don't need finite. Let me talk about hedonic model. It turned, I told you in introduction that there is basically no difference between a matching model and an hedonic model. Let me try to convince you of this. Oh, wait, before that. Remember my motivation, the reason why I started to talk about matching models to start with. Told you, okay, I know that there will be a marriage market, there will be men, there will be women, they're going to match, and as a result of this, endogenously, there will be an allocation of resources. In my case, it will be an allocation of utility. But I want this allocation of utility to be endogenous. This slide is telling you that's exactly what the model tells you. There is an allocation of utility which is compatible with stability. In some cases, there will be only one. We're going to talk about uniqueness in a minute. But this allocation is not very hard to find. You can find it as the solution of a linear programming model. So in other words, if you give me a list of people and a surplus function, I know that there is always at least one, in general exactly one, sometimes not, but I know that there is a way of allocating them so that the outcome will be stable. And in addition, I know exactly how the surplus created by each married couple has to be distributed so that I get stability, which is exactly the problem that was motivating me. So if you apply that to a marriage market, not only I will know who's going to marry whom, but I will say for this particular couple, there is one particular way of distributing the welfare between them that's compatible with stability. The stability condition will pin down the allocation within the couple. I'll be more precise in a minute, but that's my motivation. Let me move now to the hedonic model. Now, hedonic model, some of you who has worked with Jim Heckman know definitely what an hedonic model is. Now I have three sets. I have buyers, I have sellers, and I have products. Each of them has a measure mu and nu. There is no measure of the set of products for the moment. Now, you use an hedonic model in which the hedonic model have two characteristics. First of all, the population of both buyers and sellers are widely heterogeneous. So you have a lot of buyers different from each other, a lot of sellers different from each other. And the second thing is the set of products, what I call Z, is not the set of actual products, it's the set of potential products. So think, for instance, of the set of, say the set of products is the set of cars. What do I call a car? How do I define a car? Well, I can think of a list of characteristics of the car. The speed, the power, the color, the comfort, whatever. You know, you can get a list of 50, 60, maybe 100 characteristics that exactly define a car. Think of Z as a vector with 50, 60, 100 components. That's the set of all possible products. And in principle, I might be able to construct a car that have exactly any list of characteristics in this Z set. But in fact, the number of products that will be actually produced is much less than this. Only a very small number of products will be actually produced. Most of the potential product will never exist. The question is which are going to be produced. And there is an additional component which is people buy exactly one product. So people buy one car. People cannot buy 1/10 of a car. Those are products which are not divisible. So this is the general, the intuitive notion of an hedonic model. Now, what do you call an equilibrium? As always, an equilibrium, you need a price for each product, P of Z. You have quasi-linear preference of the utility of Mr. X buying a product Z depends on the product Z itself. And of course, that might depend on the characteristic of X, meaning that some people care a lot about speed and some people just care about minimum consumption, I mean minimum cost. On the other hand, you have seller. The seller maximizes the profit, and the profit they make on a car is the price at which they sell it minus the cost, and again, the cost can be producer specific. Now, what's an equilibrium? An equilibrium is a price P of Z that clears the market, but remember, I need a price not only for those commodities which are actually produced, but I need a price for all commodities that could be produced, right? Which tells you that it sounds like a simple model, but if you want to use standard technique of general equilibrium, you're in big trouble because the set of potential product is infinite. Actually, it's a continuous set. It's hard to the 100. And as you well know, the standard technique of general equilibrium do not apply to infinite number of commodities. Actually, they do not, even less to continuum of commodities. So now it happens that in the case of hedonic model, because of this quasi-linearity, proving the existence of an equilibrium and actually characterizing the equilibrium will be a piece of cake. So let me show you that this is equivalent to a matching model. Now, first of all, if you start from an hedonic model, you can easily define a matching model. Here is the way you do that. The surplus, so I want to define the surplus of buyer X when matched with producer Y, right? But I need to define which product they're going to trade. The total surplus is the utility minus the cost, because he will pay the price, the buyer will pay the price, the producer will receive the price. It's just a transfer, it doesn't enter into the sum. So it's pretty clear which product they're going to build. They're going to, if X is matched with Y, the product they're going to build is the one that maximizes the surplus here. There are two questions: which buyer will be matched with which seller, and which price am I going to charge? Now, the first thing is, if I have an equilibrium of the hedonic model, it's a stable allocation of the surplus of the matching model, and it's obvious. That comes from the definition of the surplus. What's a bit more complex is to show the opposite. Assume that I take this surplus. I take this surplus, I have my distribution on the X set and the Y set, I find a stable match. My claim is, if I have a stable match, then I have an equilibrium of the hedonic model, meaning that I'm able to find a price that clears its market. So the question is, how do I construct the price? Now, and here is what you get here in those equations. So, first of all, remember, if I have a matching model, if I have a stable match, I will have U of X, which will be the utility of the buyer at the stable match, and I will have V of Y, which will be the profit of the seller, which are such that U of X plus V of Y must be at least equal to S of XY, that's the stability condition. And then S of XY must be larger than U of XZ minus C of YZ for all Z, because that's the definition of S. S is the max, so it must be larger than any value here. Let me take this C, let me take this U, let me take this C, put it on the right-hand side, and let me take the U, put it on the right-hand side, and I have this inequality here. And that's true for any X, any Y, any Z. Now, you know that the left-hand side does not depend on X, the right-hand side does not depend on Y. So let me take a P of Z, which is between those two numbers, and it's very easy to see that this is a price, an equilibrium price for the hedonic model. Now, the good thing is, if I want to, assume that I want to prove assume that I ask you the following question. In order to prove existence of an equilibrium of the hedonic model, do I need single crossing? You know about single crossing. You know that at some point I may talk about something like the second cross derivative. And we know that in hedonic model it has been used big time. And sometimes there is a confusion. Do I need, is the single crossing property, I'm going to talk about it in a minute, but is it needed for existence? But here you see that obviously it's not. The existence comes from the fact that it's equivalent to a matching model, and the matching model is equivalent to a surplus maximization. For a surplus maximization, for the existence of a surplus maximization, I just need compactness and continuity, that's it. So I have existence in a very general framework, and the dimension of my set X, Y, Z can be anything. It can be 100, it can be actually an infinite dimension. Let me come to my single crossing condition. Now, just for a minute, I'm coming back to a situation in which everything is one-dimensional. So X is one-dimensional and Y is one-dimensional. I have the usual definition of supermodularity of the surplus function, which is here. So think of X as income and Y as income. This is telling you something that's quite familiar. Assume that I have two women, one wealthier than the other. Assume that I have two men, one wealthier than the other. The total surplus that I create by matching the wealthy people together and the poor people together is more than what I would do by mixing. That's the standard definition of supermodularity. Note that if S is twice continuously differentiable, this is equivalent to the fact that the second cross derivative of S is positive. And that's exactly what's called a Spence-Morley's or a single crossing condition, right? What does it buy me? It buys me assortativeness. It buys me the fact that the matching, in that case, the stable match is very simple. The wealthiest man will be married with the wealthiest woman. The second wealthiest man will be married with the second wealthiest woman, and so on and so forth. That's one-dimensional. Note that if I'm in a multidimensional setting, everything collapses. First of all, the supermodularity. I cannot even define the supermodularity because this inequality here cannot be given a signification if I have vectors instead of numbers, and the notion of assortativeness cannot be translated in a multidimensional framework. There is a generalization, but I won't have time to talk about this. It's in the paper that I wrote with Rob McCann and Lars Nesheim in Economic Theory, if you're interested. Now, this is the main reason why I'm interested in those models. With a continuum of agents, intra-match allocation of resources is pinned down by the equilibrium condition. So let's try to look at it, and I will convince you that not only I have an abstract result that tells me it's pinned down as being the result of the dual minimization problem. Of course, it's good to know, but if I want to construct, it will be good to have not only a theorem that tells me that those things exist, but a way to explicitly construct this allocation. Think of the models that I had before. You know, a Cobb-Douglas model in which I have private consumption, public consumption. I'm going to find with match with women, there will be exactly one allocation of utility which is compatible, but can I construct it? Can I find out how much private consumption, how much public consumption there will be there? And let me show you that not only I can do that, but it's very easy to do, and it's very easy to get a closed form solution. And this, by the way, is probably the main reason for using this TU framework. So first of all, let me take the very simple situation in which X is one-dimensional, Y is one-dimensional, S is supermodular. So I know who marries whom because there is assortative matching, and my assortative matching condition tells me that Mrs. X is matched with Mr. Y if and only if the number of women above X is exactly equal to the number of men above Y equal phi of X. That's, you know, assortative matching. Which is if I know the distribution, I can exactly find out. Now, this is the first equality on this slide is stability. Remember that U of X minus V of Y is always larger than S of XY. So it must be larger than the max. But actually it must be equal to the max because I know that the equality is reached for at least one couple, which is the couple who are married. So U of X is equal to the max being reached for the particular Y that X is going to marry. Okay? Now remember that I'm assuming that everything is continuous and differentiable. So now I can either write the envelope theorem applied to this inequality, to the equality here, or write the first order condition for this max, and I get this. U prime of X is equal to ds of dx at that point, and V prime of Y is equal to ds of dy at that point. I just put an integral. I have a closed form solution of my utility. I just need to know the shape of the surplus function, and then I can compute the utility of the wife and the utility of the husband up to two additive constants, and then I can pin down the constant using, and the way I pin down the constant is something like, assume that there are more women than men, say, then some women will not be married, and it must be the case that the last married woman is just indifferent between being married or being single. So you got the closed form solution. Now, in the particular case in which my in which my utility were Cobb-Douglas, ds was quadratic, and I have to integrate. I have to just integrate to get the utilities. I can do that numerically, or I can, in many cases, do that closed form, pinning down the constants. Let me forget that. There has been a lot of application, applied theory. This has been applied to abortion. It has been applied to children, to demand for higher education, dynamics, and so on and so forth. I won't have time to talk about all this, but let me, during the last 10 minutes, talk about a particular problem and then show you how this can be taken to data. Now, here is the problem that I'm interested in. We all know that during the last 30 or 40 years, there's been a huge increase in female education and labor supply and incomes. Look at this graph. This is the US starting in 1960 and until 2008. Blue means male, red means female, and the solid line is some college, the dashed line is college, and the dotted line is the college plus. So this is master, low degree medicine, and everything. And in each case, this is the proportion of the population aged 30 to 40 with the corresponding degree. So the first thing you see is women are now more educated than men. There are more women with some college than men. There are more women with a college degree than men. And there are more women with a college plus degree than men. That's one thing. Second thing, which is quite surprising, look at the, I'm zooming here in my rectangle here, the years between 1980 and 2006, okay, and 2008. We know that over this period there's been a huge increase in the so-called college premium. And what the college premium is defined as the wage increase that you can get from the fact that you went to college. In my case, it's not college, it's college plus, and the college plus premium has been increasing even more over the period. If the college premium increases, it means that the investment in higher education has a higher return. As economists, we believe in incentives, so we believe that if the return on investment is getting higher, then it must be the case, then people should react by investing more. And you do see that for women. The percentage here is 3%, the percentage is 11%. It's multiplied by a factor larger than 3, almost 4. That's a huge change. It's very hard to find in history a change affecting in which the percentage of the population moves from 3% to 12%. It's multiplied by a factor of 4. So we have this increase in incentives, and we see that women react a lot to that. What's somewhat surprising is that if you look at male, you don't see anything. If anything, you see a slight decrease. Now, here is the puzzle. You take men and women, not so different in principle. You face them with exactly the same incentives. And part of the population responds big time, of this kind of very strong response, and the other part just does not respond at all. How come those people faced with the same incentive are responding in those very different ways? In a theoretical paper that was published in 2009, we offer a theory. Yeah, go ahead. Question.
I just wanted to be the devil's advocate and
Yeah.
ask the question, couldn't it be so this is general equilibrium, and the skill premium has increased over this period of time, but at the same
Yes.
time, the composition of the people holding the skill has also changed. So maybe it's just so that the women are better, in the sense that then because the composition, the share of women holding the skill has increased, then the premium has increased. You're interpreting it as if the women respond more to the incentive, but it could also be due to the general equilibrium effect.
So it's general equilibrium, definitely. But the problem is, so the explanation is, women are better. But if women are better, how come at that point, in 1980, there was a college premium, not as large as that moment, but there was a college premium. There was a gain in acquiring this education. Women are better means the cost for them of acquiring this education is smaller. How come, if the cost was smaller, they did not invest more than men? You would have to tell me a story that women used to be much worse than men in the 80s, and now they are better than men. And that I don't buy. So the distribution of skill, we know things about the distribution of skills, and it's certainly the case that if you look at what we know about the distribution of skills is, for instance, distribution of SAT scores, things like this. One thing we know is that women are better than men on average. The variance is larger than men. And actually there is a paper by Gary Becker, Kevin Murphy that tried to explain this. But the fact is, it's always been the case that women were better. It was the case already in the 80s. And then the puzzle, if you wish, is the opposite. Yeah, your explanation does explain why I have more women than men here, but it's very hard to explain why women were so much underinvesting then. There are plenty of explanations. Huh? Yeah, but you know, in a sense, yes,
Yeah.
there must have been some sort of this, but you know, as an economist, if you're saying it's due to social norms, it's due to, it's not the institution in the sense there was no law prohibiting women to access universities. It could be social norms. But in a sense, as an economist, if you're saying the social norms were such and then they have changed, it means, as an economist, I have nothing to say. So, and I'm not denying that there are social norms. I believe in, no, but I believe in social norms. I think they are part of the explanation. But let me try to tell a story as an economist in which everything is endogenous as an equilibrium. Let me, maybe I should correct a little bit what I said. Economists can and should talk about social norms, but the condition should be economists should have a meta theory of the formation of social norms. And there are people working in this direction, which I find very interesting. It's fair to say that we have not yet reached a point in which we agree on this. But in a sense, by the way, my story is also about social norms. But so, oh, by the way, I need to hurry. How much time do I have? Steve?
So.
Oh, great. At some point, I thought I had only 5 minutes, so I was becoming a little bit nervous. Here is the story that we have in this paper. The impact of education is twofold. 99.5% of the literature concentrates on one impact, and the other is completely neglected despite the fact that it's extremely important. The first aspect is what we call the college premium, which is if you have a college education or college-based education, your situation on the labor market is much better. You have higher wages, lower unemployment, better career prospect, and so on and so forth. That's true, that's part of the motivation for investing, but the problem is we have no difference between men and women. If anything, we have the difference is in favor of men. So that cannot explain why we have this kind of huge difference in reaction between men and women. But there is something else, which is the marriage market. And this has several components. Depending on your level of education, the probability that you will get married is not the same. The person, the education and the income of the person with whom you get married is not the same. The surplus generated is not the same, and the division of the surplus is not the same. And that could be an important part of your decision to invest. Actually, if you look at the 19th century novels, you see plenty of this. You see plenty of stories in which women acquire an education not because they want to go on the labor market, but just because they want to find a husband. Thankfully, that's not the case now. They go to the labor market and they exploit this human capital. But still, it's certainly the case that the probability that you get married with a person with a given education has to do with your level of education, with your own level of education. Now, in the paper, we do a theoretical model in which we say, well, there is a total college premium. The gain that you get from acquiring education is the sum of the two components. And the first component is pretty much the same for men and women, but it could be the case that the second component is completely different. And in particular, the evolution over the last 40 years has been completely different. And if you accept that the marital, what we call the marital college premium, has been increasing a lot for women, but not for men, that might explain why women have been responding much more than for men. The paper is essentially theory plus a vague calibration that tells you it's a story that's consistent, and if you put the right numbers, you can tell a story that fits the data. But it's not an estimation. And now I'm going to talk about really how you estimate this kind of stuff. If you look at the theory, let me tell you just one thing about the theoretical structure, because the theoretical structure is quite interesting. First of all, you need heterogeneity. In this kind of model, if different people make different decisions, it must be because they are different to start with. So in our model, people are different in two dimensions. One is willingness to marry, and the other one is the cost of acquiring education. So it's a two-stage model. In stage one, you choose education, and you choose whether to enter on the marriage market. So some people might choose to get an education, some might not. And also some people might decide to get married, and some people might decide that they're better off being single, or they're not willing to make the kind of sacrifice that will be needed to get married. Note that those two decisions are linked. If you if you're a big fan of marriage, then it makes all the more sense to invest in education for a given level of cost of acquiring, because you will receive the marital college premium in addition to the labor market college premium. If you're sure right from the beginning, yeah.
Can I ask what's
Yes.
homogeneous then in this? So what are we assuming is the same across individuals? Is it preferences?
So the theoretical model, you have a joint random distribution of two characteristics. One is the cost of acquiring education, and the other one is the willingness to marry for men and for women. So we have two distributions, a two-dimensional distribution on each side of the market. Now the resolution goes backward. You start with the matching game. Assume that people have made their investment decision. This gives you distribution of a number of educated and uneducated people on both sides of the market, and then they match. You solve the matching game. Once you solve the matching game, this tells you who marries whom, but more importantly, it tells you how the surplus will be distributed. How the surplus will be distributed as a function of your education, of course. And that's crucial because that's what motivates your investment in the first period. So you solve it backward. Solving the second period will tell you what will be the reward of your education, in the sense that it will tell you how much of the surplus you will get if you're educated and how much of the surplus you would have gotten without being educated. And again, and then in turn, you will replug that into the first period model, and this is what motivates the decision to invest in the first period. It's the standard rational expectation model, right? So it's the fixed point. Note that it's a fixed point in a functional space. What you have in mind is a distribution of education for men and women on both sides of the market as it will take place 10 years from now. You have this in mind since this generates a particular matching game that generates some rewards to education. Because you have this in mind, you have those rewards to your education in mind, this generates your decision to get an education. And the fixed point is the distribution that you have in mind is exactly the same as the one that is generated by the education decision triggered by this representation. So it's the fixed point. And the question is, how do you take that to data? Now, there are some kind of general consideration about how you take matching model to data, but I'm going to skip that for the moment. And then I'm going to show you an empirical model that will be used to take that to data. Let me start with a general introduction about the econometrics of matching. Take a simple model in which there is only one dimension of heterogeneity, which is in my case education. It could be income, but there is only one dimension, okay? Those matching models, they give you very simplistic prediction. Assortative matching. Assortative matching means the one wealthiest man marries the one wealthiest woman, the second wealthiest man marries the second wealthiest woman, and so on and so forth. Of course, we don't see that on the data. We see assortative matching in the sense that we do see a lot of correlation. And actually, there's been this argument that the correlation between male earning and female earning have been increasing throughout time. And by the way, this has had an impact on inequality. So we see correlation. The correlation is not equal to 1. So we have to reconcile our kind of very simplistic model with the fact that there are some very wealthy men or very educated men that marry less educated, much less educated, or much less wealthy women, and so on and so forth. How do you reconcile the theory with the facts? One way is to use a search model. So to say, in principle, the discrepancy is due to frictions. That's one way that I'm not talking about here, but which is quite interesting. I'm going to talk about another way, which is matching is multidimensional. Some of the dimension we observe, in our case education, but some of the dimension we do not observe. But people observe and people match on this. So the reason why I see a very educated women marrying a much less educated men is because there is one characteristic that I don't observe, And it so happens that given both characteristics, the one I observe education and the one I don't observe, that was a stable match. But of course, there is no way I can see that because I don't observe it. So the question is, how can I take to the data? So let me rephrase that in a way which would be completely familiar to anyone doing empirical macro. There is an observed heterogeneity. In my model, there is an observed heterogeneity. I need to introduce this kind of an observed heterogeneity. And the question is this an observed heterogeneity? How can I introduce it? How can I estimate the model? And can I reconcile the model with the data? Can I estimate the model and the usual thing? So all about what I'm going to present now is about what's the right way of introducing an observed heterogeneity in the model. Okay, that's the empirical model. I have a finite number of classes essentially because I'm talking about education, and we're going to talk about, ideally, we're going to talk about high school dropout, high school, some college, and college plus, 5 classes. What the result that I'm going to show you are the preliminary result with only 3 classes, but at some point we're still working on 5 classes. And by the way, when I say we, it's with Bernard Salani and Yoram Weiss. Now, I want to put on an observed heterogeneity, and here my toolkit will be the IO literature. I will use the random preferences kind of toolkit. So let me take Mrs. I, who belongs to some education class, capital I. The utility has 2 components. One component which is deterministic, which depends on private good, public good, in exactly the same way as we saw in the collective model, in the transferable utility version of the collective model. So in the end, there will be an economic component to the surplus, which will essentially depend on income. And then I have a second component, which is the random component, which is the preference shock, the preference heterogeneity, if you wish. And that's a vector. So I'm talking about women. It's the vector that has as many components as male education class. Now, the intuition is the following. You're a woman. You're born, or you draw randomly a series of n number, and this alpha I n is your idiosyncratic preference for an educated man. So it might be that 2 women might be identical in terms of education, but one of them puts a lot of weight on the idea that she really wants to marry someone educated. Let's say, you know, she loves music, and the only way she can think of life is with someone who is a professional musician, or you know, whereas somebody else doesn't really care. She wants someone who enjoys nature and sport, and whether the person is educated or not, she doesn't really care. That's the idiosyncratic shock. It has n components. Now, the crucial thing is those components are not independent of your own education. Because remember, your own education is endogenous. So if you draw this kind of vector and you end up with a vector alpha in, which is very large, so you really want to marry someone educated, then you better choose a high level of education yourself, meaning that among the people who are educated, you expect to have much larger alpha in than among the people who are not uneducated. But you will have distribution in all cases. Okay? You do the same for men, and then you're saying the sum, so the total surplus will be a deterministic part and a stochastic part, which depends on those 2, on the shock of the wife and the shock of the husband. Now, what about the deterministic part? It's very easy. They match after education has been chosen, but before income unknown. So given your education, there will be an income process that will go 1 minute, and I take the question. Given the level of education, there will be an income process which is random, which will take place throughout the life. There is no divorce in my model. That will be for future work. And of course, by the moment you marry, you have no idea what the process will be. So you don't have an idea of what the income will be. So the only thing you can do is compute the expected. So you cannot compute you don't know what the surplus will be, because the surplus will depend on the realization of income. But what you can compute is the expected value of the surplus, conditional on the level of education. And that's what I'm going to call the deterministic part of the utility function. Yes, there was a question. Well, it's easier with the mic, and the sound is not great on my side.
Yeah. So I was just wondering, I was kind of expecting you to set it up a little differently, where instead of having people have idiosyncratic preferences across the different education classes, instead people just have some kind of like beauty factor. And you know, the reason why you might see someone end up with someone not in their education class is because that person was kind of hot or attractive or something. And I was wondering if the reason why you didn't set it up that other way, which seems in some ways simpler, because it's just one shock, was because that would actually affect the education choice in the first stage. Because then you would have people who are very attractive saying, oh, I don't have to go to college because I can meet someone without doing all that. Was that why? Or so why'd you set it up this way and not that other way?
Look, there are two things. First of all, it's not incompatible with my model. The alpha could be linked with physical attractiveness, and in which case you might say, you know, physical attractiveness has nothing to do with college, which means that essentially the alpha will be the same. That's not incompatible. What I'm ruling out, I mean, I'm ruling out something which is a match-specific shock. I have individual-specific shocks on both sides. In general, I allow them to depend on the education of the. See, at the end of the day, I'm interested in data like, is it how many people from one class of education marry people from the other class of education? So it's most of the action that I don't observe is linked to things which are completely orthogonal to education. That's fine, that's compatible with my model. Probably it will not help me much in my explanation, but in principle it should be testable, right? Because it would be something like within the class of education, you know, there should be some randomness. The fact that an educated person marries an uneducated person has nothing to do with the level of education. It has to do with attractiveness, which is distributed independently. You know, then it's a particular specification of this model that should lead to testable implications. So in principle, what you suggest is a particular case of this. I'm just allowing it to depend also on the education class. There is an additional thing that I should say, which is, so my total surplus is my deterministic component, and then those two idiosyncratic components, one which is indexed by small I, which is of the woman, and is specific to the education class of the husband, and the other one which is specific to the husband, so it's the small j, and it depends on the education class of the wife. What I don't have is an epsilon ij. So what I don't put is the fact that attractive people like attractive people. You know, that there is some additional surplus. Think of a situation in which everybody like attractive, but the fact that the wife is attractive is much more important if yourself you're attractive. Something like supermodularity in attractiveness. That's not in my model. That's explicitly excluded from my model. So in that sense, I'm not going exactly as far as I could in the direction you suggest. The reason for doing this is really parsimony. That remember that attractiveness is something that's not in my data. So I don't want to start modeling specific supermodularity, which makes things more complex, in a characteristic that I don't observe for the husband and I don't observe for the wife. Because, you know, that's really going to make my identification strategy much more problematic. So that's the one thing that I'm assuming away. Okay, now we have a theorem that tells us that the utility that Mrs. I will get is the sum of two components, a deterministic component, which is here, and a stochastic component, which is exactly your own idiosyncratic shock. And that, by the way, those of you who are familiar with the empirical IO literature, it's very similar. That, you know, you buy a particular type of car because your idiosyncratic preference is that you like a lot fast car, so you will end up buying a fast car, and the utility that you will get is whatever deterministic fact there is, namely the price, the quality, the car, the price you pay for the car, and so on. And then there will be the additional idiosyncratic component, which is your own utility from this particular characteristic. So that's exactly the same kind of spirit. Now, what's very cool here is that, remember, my utility UI is this deterministic stuff plus my idiosyncratic components. That's if I marry someone with category J, but of course I can compute this number for each possible category J, and I can also compute this number for remaining single, in which case this alpha will be 0, will be normalized to 0. And then the question is which choice I'm going to make, which J am I going to choose? But the answer is simply, I'm going to choose the J that gives me the largest possible value for this UI. Now, if you look at this, so essentially, if I belong to class, if a woman belonging to class I, if a woman I belongs to class capital I, she will be matching the spouse in J if the utility she gets from marrying someone in J, which is this guy here, is more than the utility that you would get from marrying somebody from any other class, and is more than the utility that you will get from remaining single. This is a standard discrete choice model. This is just, you know, a standard logic model a la McFadden. So this tells you that you can use the technology of discrete choice model in this kind of framework. It's not a simple discrete choice model because you have a bunch of discrete choice for women belonging to each category. So you got, in a sense, you have a logic for if you look at things from women's point of view, you have a logic for each class of education, and you have the same on the other side. And you have a compatibility condition between the two logics. But still, it boils down to logic model, which makes your life much simpler. Now, there are plenty of things about identification. The model, in principle, is exactly, so in principle, the model is exactly identified. I mean, that was done in a paper by Chu and Sayo in 2006. The problem is the model is exactly identified, which is not very nice because you cannot test it. In a sense, you have identification problem. The model is somewhat under-identified. So again, we're going to use a solution which is exactly again, borrowed from the IO literature, which is, I will consider several markets. Now, those of you who are familiar with the industrial organization empirical literature, there are two types of models in which you have one market and one models in which you have plenty of markets. If you have plenty of markets, in which, with some kind of structure, like the distribution of preference is the same across markets, but the distribution of supply, distribution of producer, for instance, is different across market, you get a lot of identification power coming from this. Right? And so that's exactly what we're going to do. And the markets, in our case, will be cohorts. So we're going to look at all those cohorts, starting from the people born in 1950 and ending up with the people born in 1980 or 1990. And we're going to say those cohorts were facing completely different market situation. So the outcome, the realized match are completely different because of this. However, there is something in common between those various cohorts, and we need to define what was common. One temptation would be to say the deterministic parts and the distribution of the alpha was the same across cohorts. The only thing that varies across cohorts is the fact that the marginal distribution has changed. That's not what we're going to do. We're going to have a much more general model in which, so remember, this capital Z is the distribution, is the deterministic part of the surplus. C is the index of a cohort. And what I'm going to say is the surplus generated by marriage may have changed over time. By the way, we know that the surplus generated by marriage has varied over time. We know that it has decreased. We know that because the number of marriages have been going down big time. There is a lot of action on this dimension. And in principle, the decrease might be education specific. So it might be that the decrease in the value of education has decreased much more. In the value of marriage has decreased much more or much less for educated men. It must be the same for women. Look at this assumption that I'm making here. I'm allowing for any kind of male education specific trend on the value of marriage. I'm allowing for any kind of female education specific trend on the value of marriage. But I'm not allowing interaction, which means essentially that I'm assuming, which is the equation here, that the supermodularity of the deterministic part has not changed over time. So my identifying assumption is the preferences for assortative matching have not changed over time. Remember, what drives the assortativeness of the matching is the supermodularity. The preference for marriage has changed, may have changed, and actually the data will tell us they have changed big time. They have declined for everyone, and they have declined in completely different way for educated people and for uneducated people. But the supermodularity did not change. That's the model, and then it so happened that the model is over-identified. Now, if you give me 1 minute, I have some slides that I just realized that I didn't take exactly the right slides. There is a graph that I want to show you. So give me just 1 minute. Okay. First of all, we're almost over. So what I'm going to do now is tell you a story and show you numbers. Here is the story. I tried to explain the fact that we had a theoretical model suggesting that the marital college premium has been evolving in a completely different way for men and women. So essentially our explanation of this difference in investment is what you get if you invest in education, what you get on the labor market is pretty much the same if you are a man or a woman, so this cannot explain the difference between genders. But what you get on the marriage market is completely different, depending on whether you're a man or a woman. About a year ago, I was at a dinner, and I had the privilege to be sitting next to Bobby Solow. She's the wife of Bob Solow. You know about Bob Solow, right? He's an economist. What you might not know is that Bob's wife, Bobby, is also an economist. She's old now. She must be in her 80s, I guess. But she's a very remarkable person. And we started chatting about those notions of education, women, and so on and so forth. And she's a complete counterexample of everything we know about the relationship between gender education back in the 50s. What we know, what data tell us, is what happened in the 60s, in the 50s. First of all, women were very unlikely to get a PhD. The proportion of women with a PhD was much, much smaller than men. Second, if they had a PhD, they were unlikely to marry. Actually, women with a PhD has a 50% probability of marrying, whereas women with a high school diploma has a 90% probability of marrying. Third, when they were marrying, they were unlikely to have children. And fourth, when they had children, they were very likely to stop working. Those are patterns that you have big time in the data, and she was an exact counterexample to that because she got a PhD, she got married, she had children, and she continued working. So I started talking to her, and she said, and then we talked about my paper, and I started to explain the paper to her, this idea, of marital college premium, the fact that the marital prospect have evolved in a completely different way between women and men. And I tried, explain that in a somewhat clumsy way. And at some point she stopped me and she said, let me try to summarize your paper, see if I understood it. In my time, she says, it was okay to be a nurse because you had a high probability of marrying a surgeon. Nowadays, if you're a nurse, forget about marrying a surgeon, you will have too much competition from female surgeons. In a sense, that's exactly what the kind of story that our paper is telling. from the female point of view, back in the 50s, not being educated was not so damaging in terms of marital prospect, because educated female were in such a small minority on the market that even women with less education has still a very high probability of marrying up. Now it's much less the case. If you look at men, it's just the opposite. In a minute, I'm going to show you data that will convince you that it's exactly in the data and it's there back time. But if you think in terms of incentives, back in the 50s, it was okay for a wife could afford, even if you really wanted to marry an educated man, you could afford not to be educated yourself. Now, if you want to marry an educated man, it's almost indispensable to marry an educated person. And marrying an educated person has a lot of economic advantage, higher income, higher surplus, and so on and so forth. So in other words, the cost in terms of marital strategy, of being educated now, is much higher for women than it used to be back in the past. And you don't see anything like this for men. If anything, you see the opposite. You get the story? Now let's look at data. Look at this graph. I'm taking two generations of this is women only. On the left-hand side, I have the generation born in 45, and the right-hand side, I have the generation born 30 years later in 75. Now, each row corresponds to a level of education of women. I'm just talking about women. So at the bottom, I have women who are high school dropouts, some high school graduates, some college, and college plus. The colors here are the education of the husband. So the light blue is college plus, the blue is college, the green is some college, the orange is high school graduate, and the gray is high school dropout. Now look, for instance, here. Women with some college, that will be my nurse. What's the probability that she will marry a surgeon, a man with college plus? Well, it's not huge, but it's a good 20%. That's the old generation, the generation born in 45. Now, it's 5%. The probability that you will marry to the top, given that you have an education which is at some intermediate level, has been divided by a factor of 4. If you look, even if you have a college, which was a rare event for this generation, but the probability that you will marry either up or at the same level was something like 80%, and in particular, you had a good 45% probability of marrying up. Now the probability of marrying up is only 20%, and actually the probability of marrying down to a husband less educated has increased. Another pattern is the length of each rectangle here is proportional to the probability of getting married. So you see a very distinguished, a very specific pattern of this generation, which is that if you have a college plus, you are less likely to get married at all than anything else. I mean, you are basically neck to neck with high school dropout, and you are much less likely to get married if you are the college plus than if you are a high school graduate. Now it's the opposite. Those two are neck to neck, and it's much better than anything else. What this tells you is that the benefits on the marriage market from being educated, or if you wish, the cost of being less educated, have increased a lot for women. Let's look at what we have for men. For men, it's just the opposite story. The probability of marrying up, if anything, has increased. Now, there is no miracle here. In a sense, it's the self-fulfillingness of the equilibrium. If you move from a world in which very few women were educated to a world in which most women are educated. So it's not surprising that now it's much harder for women who are not educated to marry up, and it's much easier for men who are less educated to marry up. But, you know, that's confirmed big time in the data. What the model that I showed you does is just give a structural version of this, while a semi-structural, semi-reduced form version of this. The model is identified, and let me conclude too. And let me come back to this now. So I was telling when I was trying to introduce this stuff, I was saying there are plenty of benefits that you can get from getting a college, getting a college degree on the marriage market. It increases your marriage probability, it increases the whom you're going to marry, it increases the surplus, and it increases the distribution of the surplus. The first two you can observe in the data. The last two, it's not observing the data. You need the model, but the model that I showed you exactly gives you this. So you can compute all those probabilities, and then you can do better than this. You can compute the marital college premium. And that's the marital college premium we get from our model. Red is for men, and green is for women. Now, this has nothing to do with modeling the demand for education. This is just identified from the marital patterns. But what you see, the marital patterns tells you, which is pretty much, which was already implicitly part of the story was in the graph that I showed you before, but it's that if anything, for men, it did not change, it's flat, whereas for women, it did increase big time. Now, what's the conclusion here? There are plenty of extension and empirical application that I don't have time to do, but just to conclude, there is something that has to do with inequality within the house. There are various ways in which we can address it. In the first part of the presentation, I showed you models that look at demand function, look at economic behavior, and try to infer the level of inequality from economic behavior. And the good news is you can get a lot. You have to make assumption, and it's important to understand the assumption, what they buy, what they cost, but you can do a lot. The second part of the talk was a bit more structural, a bit more theoretical. The idea was, can we write an equilibrium model in which this distribution of power will be endogenous? I have to apologize. I presented in 1 hour something that in principle should take like 4 or 5 hours to be presented. So I did not have time to enter into the details, and it was a bit rushed. And at the end of the day, you might have missed some of the details, but there is a reading list, so you can go to the papers and see what's going on. But hopefully the one thing I convinced you of is, do we have the technology to write matching models? And those matching models will tell us not only who marries whom, but much more interestingly, how is the surplus generated by marriage distributed? And this distribution will be endogenous, will be driven by the equilibrium condition, so that if you look at the situation in which there is a lot of evolution and the number of educated women increase a lot, those models will tell you what the impact this will have on the intra-household allocation of welfare, utility, resources, and everything. And of course, in turns, this tells you you can close the model by saying, but this increased gain might be the motivation for the increase in education that we observe. My goal was to attract your attention on a set of models, on a particular technology, and convince you that there might be something interesting in the sense that there is a technology that's now start to be well known and that can be widely used. That was my point, and thank you for your attention. You guys must be willing to go for lunch. I am personally willing to go for dinner, but are there questions? Yeah, there are worse things in life than dinner in Paris. Questions? No, I can postpone my dinner by a few questions, if needed. No questions? Okay, enjoy the Chicago lunch, and thank you very much for this very pleasant time with you guys. Bye-bye.